Welcome to The Explainer. Today, we're going to get into a concept that's really at the heart of chemistry and energy, enthalpy. You ever wonder about this? Why does a campfire feel so warm, but one of those instant cold packs feels freezing to the touch? It's a pretty simple question, but it has a really powerful scientific answer. And it all boils down to this one crucial idea, enthalpy.
So, what exactly is this thing, enthalpy? Well, put simply, it's how we measure the total heat energy that's packed inside a system.
Okay, so the official definition of enthalpy, which we represent with a capital H, is the total heat content of a system. It's made up of two key parts. First, the system's internal energy. You can just picture that as all the energy of its molecules zipping and bouncing around. And second, the energy the system uses just to take up space. Think of it like the energy cost for making room for itself in the universe. And that gives us this foundational equation, H equals U plus PV. Now don't worry, we're not going to be doing a bunch of math today. The point of seeing this is just to remember that enthalpy isn't only about the internal heat of something. It also has to account for the physical space it occupies. This little formula is our key to unlocking the energy changes we see all around us.
All right, so we've got our definition, but here's a little secret in the world of chemistry. We almost never talk about the total enthalpy of a system. Why not? Well, because it's incredibly difficult, almost impossible to measure. Instead, we focus on something way more useful, the change in enthalpy. It's not about where you are, it's all about how far you've come. And this is exactly how we track it. You see that little triangle? That's the Greek letter delta. And in science, it just means change in. So delta H is simply the final enthalpy, H2, minus the initial enthalpy, H1. We are literally just measuring the difference between the finish line and the starting point of a process. That's it. Now, this whole idea leads us to the single most important property of enthalpy. It's what we call a state function. I know, it sounds a little technical, but what on earth does that actually mean? Let's use an analogy to make this super clear. Imagine you're hiking up a mountain. A path function is like the total distance you walked. It totally depends on whether you took the long, winding scenic route or the super steep direct path. But a state function, that's just your change in altitude. It doesn't matter how you got to the summit. The only thing that matters is that you started at the bottom and you ended at the top. That's enthalpy. It only cares about the starting line and the finish line. And trust me, this is a total game changer of an idea, and we're about to see why. So let's see how this concept actually works in the real world, starting with some simple physical changes. Like stuff changing from a solid to a liquid, or a liquid to a gas. We can measure the enthalpy change for three of these key transformations. There's fusion, which is just a fancy word for melting, vaporization, which, you guessed it, is boiling, and sublimation, which is that weird one where a solid turns directly into a gas. Let's just focus on fusion for a second. This is the precise amount of energy needed to melt exactly 1 mole of something, and a mole is just a standard quantity that chemists use, kind of like how a baker uses a dozen. So for ice turning into water, this is the energy required to break apart all those rigid ice crystals, letting the molecules finally flow freely as a liquid. And this is where it all comes together so beautifully. Since we know enthalpy is a state function, the energy you need to go directly from a solid to a gas, that's sublimation, is exactly the same as the energy you'd need to first melt it and then boil it. The path just doesn't matter, only the start, a solid, and the end, a gas. Pretty neat, right? Okay, so physical changes are one thing, but where enthalpy really shines is in explaining the energy flow of chemical reactions. This is really the core of a field we call thermochemistry. And you're going to notice a pattern here. Just like before, we're calculating a change. The enthalpy change for a reaction, or delta RH, is just the total enthalpy of all the products you made minus the total enthalpy of all the reactants you started with. It's that same final minus initial calculation all over again. And this simple subtraction gives us two possible outcomes that, believe it or not, answer our very first question. If the products have more energy than the reactants, the system has to absorb heat from its surroundings to make that happen. That's an endothermic reaction, and it feels cold. The delta RH is positive, but if the products have less energy, the system releases all that extra heat. That's an exothermic reaction. It feels hot, and its delta RH is negative. Your campfire is exothermic, and that instant cold pack is endothermic. It's as simple as that. All right, now for the big payoff. Remember how I said that enthalpy being a state function was a game changer? This is exactly why. It gives chemists a kind of superpower, a brilliant shortcut known as Hess's law. Hess's law basically states that if a reaction happens in a few different steps, the total enthalpy change for the whole shebang is just the sum of the changes for each individual step. And why does this work? Because enthalpy is a state function. The specific route just doesn't matter. This is incredibly powerful. Imagine you need to know the energy change for a reaction that's maybe way too slow or even too dangerous to measure directly, like going from A to C. Well, if you already know the energy to go from A to B, and you know the energy for B to C, you can just add them up. It's just like calculating the total altitude gain of that mountain climb by adding up the gains from smaller, easier trails. It lets chemists predict the energy of reactions without ever running them in a lab.
So, in the end, enthalpy isn't just some abstract concept in a textbook. It's the invisible force driving the heat of a flame, the chill of an ice pack, and even the energy in our food. The next time you feel something get hot or cold, you'll know it's all about the change in H.